Hi, my name is Brian Caffo, and I'm going to talk today about statistical linear regression models. And I want to emphasize the term statistical because in this lecture we're going to start talking about a little bit about inference. And this class is co-taught with my colleagues Jeff Leake and Roger Peng, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so previously we talked about least squares, and our way of getting regression lines was really to think of it as a math problem, that I had a bunch of points in Cartesian coordinates, right? And I just wanted to find the line that minimized the sum of the squared vertical distances between the points in the line. But that's not a statistical model, okay? So why don't we try to formalize this with a statistical model? Why don't we say that our y's, our outcomes for person I or measurement I, is a line, beta naught plus beta 1i, then plus a random error term where the error terms are assumed to be IID, and it's not necessary to assume they're Gaussian for all parts of what we're doing, but we're going to frequently rely on Gaussianity of the errors. Now that's a much more that adds a lot of assumptions over what we've been thinking about previously, but hopefully we get something for that. This we think of this as sort of the sampling model, right? We're thinking that our errors are independently and identically distributed, and this is sort of the kind of mechanistic part. So as a consequence of this, what we wind up with is that the conditional expected value of the y's given the x's let me call that mu I, meaning that ith conditional mean, works out to be beta naught plus beta 1 xi, right? And that's easy to see because if I just take an expected value, I'm not going to write the conditioning on x part here. Expected value over here, since we're conditioning on x, all that part's none of it's random, so we have beta naught plus beta 1 xi plus the expected value of the epsilon i's, but those are 0 because of this assumption right there. Okay. The variance then works out to be sigma squared, which also you can see pretty easily. Variance of yi is exactly the variance of this equation, but all of that, we're conditioning on xi, which again I'm not writing. All of that is just a constant, so the variance of this whole thing is just the variance of epsilon because the rest of it's just shifting it around, okay, and that works out to be sigma squared, just again by that assumption. So this is equivalent, if we assume, now we're going to rely on our normality, if we assume that not only the epsilons are IID with 0 mean and variance of sigma squared, if we actually assume that they're normal, then this model right here yields the same likelihood as if we were to simply assume that the y's were normal mu I sigma squared and that the mu i's satisfied that relationship right there. Okay, so since we have a likelihood, we can do maximum likelihood. Let's write out our likelihood first, and hopefully you've taken the inference class. If you haven't, again, this class we're not going to focus on the mathematics, but for those of you who have taken the inference class, I'm going to show you some of the details. If you haven't, then maybe just listen or maybe skip a slide or two. We won't be quizzing or testing a lot on this kind of questions. So here's the likelihood. The likelihood is a bivariate likelihood, and it involves both beta, the slope parameters, which I'm concatenating beta as equal to beta naught and beta 1. So I guess it's a trivariate likelihood. It has the beta parameters and then the sigma parameters as well. But notice, okay, so as is often the case, we log likelihoods because this product's kind of annoying. So why don't we log it? And here by log I mean natural log. And then because of that guy and that guy, it's always good to take a minus twice the log likelihood. So maximizing the likelihood then is going to be equivalent to minimizing minus twice the log likelihood. Okay, and look at minus twice the log likelihood, then it turns out to be that guy right there. And, we're here again, remember mu I satisfies this guy. So if we want to minimize this equation with respect to beta naught and beta 1, where beta naught and beta 1 are embedded in this mu I right there. If we want to minimize it, notice it doesn't actually depend on sigma. And so if we can just minimize for beta naught and beta 1, that guy right there, we'll have minimized it overall, regardless of sigma. Now we'll have to figure out something else to get an estimate for sigma squared, but for beta naught and beta 1, if we can minimize that, then we're fine. Well, notice that's just exactly the least squares criteria that we minimized to get beta naught and beta 1 from before. So it turns out that under Gaussian errors, our linear regression model, the maximum likelihood estimates for the slope and the intercept are exactly the same thing as the least squares estimates. Okay, and then let's recap what those estimates worked out to be. So our estimate of beta 1 worked out to be this guy, right, where the correlation times the ratio of the standard deviations, and our beta naught hat satisfied this, beta y bar minus beta 1 hat x bar. So and then remember, we've already stated those things in the previous slide. Okay, so that's a bit of a recap. So this helps us interpret some of these quantities, because I think part of the key of linear models and linear regression is that the coefficients are very interpretable. So take beta naught as an example. What is beta naught interpreted as? It's the expected response when the predictor happens to be 0. So I would write that like this: the expected y given x equals 0. And of course that's, you know, our expected y given any value of x is beta naught plus beta 1x. So of course if we plug in x equals 0, we get beta naught. So the interpretation of beta naught is the expected beta, the expected response when the regressor is 0. But no, this isn't always of interest. So if x equal to 0 is impossible, or it's way far outside the range of the data, in our height example, that was of course the case, right? No one as an adult is of height 0, right? You know, or even no one is ever of height 0. So it doesn't make any sense to interpret the intercept then. So there's a trick so that you can get the intercept to be interpretable, but not tinker around with the slopes. So here's our model, y equal beta naught plus beta 1 xi plus epsilon I. Let's imagine if I shifted xi by amount a, right? And then I subtracted a beta 1a right there, and then I have to add a beta 1a right there. Then I wind up with the same exact model, right? Beta 1 times the shifted x, right? So the slope hasn't changed, but the intercept has changed. So now the intercept is the intercept you would interpret when this new variable xi minus a is 0, or in other words, when xi actually takes on the value a. So if you take your regressors and shift them by value a, then that simply changes the interpretation of the intercept, but it won't change your slope. And often what you do is you set a to be the average of the x's, so the intercept is interpreted as the expected response at the average x value in your data. And so that's how you can often shift your data so that your intercept actually has meaning. Okay, let's talk about interpreting the slope now. So imagine if we took the expected value y given x, took the specific value x plus 1 minus the expected value y given x took the specific value x, right? So that would be beta naught plus beta 1 times x plus 1 minus beta naught plus beta 1x. Do the arithmetic out, that's beta 1. So if we look and read and interpret this guy correctly, that is that beta 1 is the expected change in the response per 1 unit change in the predictor. Okay? So let's talk about, we talked about what shifting x does. Shifting x doesn't change the slope, it only changes the intercept, of course. And so what happens if we do some sort of unit change of the x by some multiplication? So we have yi equals beta naught plus beta 1 xi plus error, okay? And then we multiply and divide by an a. Then we wind up with the same regression model, but now x times a as the predictor and beta 1 tilde as our slope, where beta 1 tilde is beta 1 divided by a. Okay? And so this is pretty easy. So multiplication of x by a factor of a results in dividing the coefficient by a factor of a. So it's a little bit easy to get messed up in these calculations. So, but if you keep track of the units, then it's easy. So as an example, if x is height in meters and y is weight in kilograms, then beta 1, which is a slope, has to be in units of y per unit of x, so kilograms per meter. Converting x to centimeters implies multiplying x by 100, right? And then to get beta 1 in the right units, we have to divide it by 100, okay? And so here's the unit discussion right here. We have x meters times 100 centimeters in 1 meter, winds up with 100x centimeters. And beta 1, which is in kilograms per meter, times 1 meter in 100 centimeters, works out to be beta 1 over 100 in kilograms per centimeter. So if you keep track of your units, you can't mess it up. So we could use our regression equation for prediction at a particular value of x. All we have to do, our predicted value of x, let's just say y hat is equal to beta naught hat plus beta 1 hat times x. Just plug in that value of x. So I don't know, we should call it maybe y hat of x. Notice at the particular observed value of x is we automatically get these y hat i's if we plug in the observed xi's. And it is in fact the difference between the y hat i's and the y i's, the sum of the squared distances, where the y hat i's live in the space governed by that regression line, is what we're trying to minimize. So here's a nice data set to play around with, the diamond data set from using R. It's the diamond prices in Singapore dollars versus diamond weight in carats. Carats is a standard measure of diamond mass. I guess I didn't know this, but 0.2 grams. You can use library R and data diamond to library using R and data diamond to get the data set. So here we can create our plot. I think all this we covered before, except this statement right here, right? So our LM price is our outcome, carat is our predictor. We want to figure out how big is the rock, how much does it predict its price. Too much, right? So data equal diamond just says that diamond is the data set that we're grabbing the variables from. AB line, notice if you plug a linear regression to AB line, it just adds it to the plot. LWD is line width, and 2 means twice as wide as the as it would normally plot the line. There we go. This is a nice regression relationship, right? Everything falls neatly on a line. Apparently, people value diamonds mostly with respect to their mass. Okay? So I don't think there's much to add there. Okay, so here I'm just refitting it. Ideally, you should only fit it once. I keep fitting it because it's so small. It only takes a fraction of a second to fit. So here I assign the output of LM to a variable called fit that contains lots of information about the fit, keeps the original x's, and so on. Coef is a function in R that'll grab the coefficients. There's our coefficients. So we estimated an expected 3,721 Singapore dollar increase for every carat increase in the mass of the diamond. The intercept is the expected price at a 0 carat diamond, which of course doesn't make a lot of sense, right? Crazy values at the intercept because you haven't collected any data near a 0 carat diamond. So what we could do, of course, is subtract this this I function here just means do this operation in the linear model. It means, I don't know, I guess execute the operation. So I caret minus mean caret just centers the data. So now the intercept has a little bit more meaning, and so now the intercept, if we get the fit, I assign this to fit 2, now coef of fit 2 is 500. $501 in Singapore dollars is the expected price for the average size diamond in the data, which is 0.2 carats. Okay, so now we've kind of created a meaningful intercept. So a 1 carat increase in a diamond is actually pretty big, I guess. I don't know a lot about diamonds, but it seems like, given the range of the data. So what about changing the units to 1/10 of a carat? So we can just do this by dividing the coefficient by 10. So if you look back, right, it was 3,721. So we can say we would expect a $370 change for every 1/10 of a carat increase in mass of the diamond. So that's much easier, and again, you can do that without having to refit the model. But of course, you could refit the model, right? And I just show you this right here. By now, instead of instead of putting carat in the model, I put in carat times 10, right? And you get the coefficient, right, appropriately divided by 10. Okay, so now let's predict the price of a diamond. Let's suppose you would fit this relationship. It seemed pretty good. Now someone comes to you and says, well, I got a couple of values of carats, and I want to predict what price I should get, so I know how to haggle correctly or whatever. So they say I want the predictive values for those 3 things. Well, you could, grab the intercept and grab the slope and multiply them times the new x's, and you get your 3 predicted dollar amounts. Fortunately, R gives you a nice predict function. You say predict, fit is the what we assign the fit to, and then new data is the data that you want the predictions at. And so you want it to be in a data frame, and the variable name needs to be the same as the variable name from the regression. So so here's new x is the name of the three numbers that I wanted to get predictions at. So I'm going to rename that vector as carat in my data frame, and so now when it does predict, it knows what variable to look for to plug into, and then you can see you get the same numbers there as you do there. And so what is this doing? Let's just draw a picture. Okay, so let's take this 0.16 one. It's saying here's 0.16. Oh, I need my pen. Here's 0.16. Here's my fitted regression line. Here's my dollar amount. Okay. Now notice that each of these red points, right? That's where we actually observe data. So the red points are the predicted ones, and the blue points are the actual observed ones. So the least squares criteria is trying to minimize the distance, the vertical distance between the blue points and the red points.